Now it's time to conclude the LOCOS fabrication flow. So we left off having created the N plus and P plus areas for contacts and for sources and drains. Let's move on to metallization, which is creation of metal wires. First we apply a mask called the contact mask, and the contact mask will create contacts between metal wires and polysilicon and N plus and P plus areas. So we grow oxide again on top of the wafer. In this case, we are going to use CVD to deposit oxide. The oxide is not going to be even. We have to planarize it using CMP, otherwise we'll have real trouble forming the metal wires. Then we apply photoresist, we expose the photoresist, and we develop the photoresist. The areas with the small transparent squares are obviously going to be contacts. They're going to be areas where the metal wires are going to make a dive down to make contact with the N plus and P plus areas. So we have to etch the silicon dioxide under the exposed photoresist or under the developed photoresist. So we are going to use wet etching to open contacts through the silicon dioxide. This step is kind of challenging because we have to time it right. We have to bathe the wafer long enough so that we have opened all the way through down to the N plus and P plus areas. On the other hand, remember that wet etching is also going to eat laterally, so the drawing that we are using here is ideal, and the real situation is going to also open up laterally. The longer we expose the wafer to the etchant, the more lateral etching there will be. So the deeper the contact, the harder it is to make. At this step, it's very important to move on very quickly because the surface of the wafer is exposed in the areas we have opened. When the wafer is left exposed, it will grow a very thin layer of native oxide on top of these exposed areas. If it manages to do so, then the contacts that we will make with the metal wires will have an extremely high resistance. So we have to move real quick, and we will use sputtering, physical vapor deposition to lay a very thick layer of metal. In this case, it's aluminum. And if the film is even or regular, that's fine. If it is not regular, we'll use CMP to polish it and create a regular surface. Then we will expose the wafer through the metal 1 mask. This is the metal 1 mask. The areas which are opaque show the silhouette of the metal 1 wires that we want to make. The areas that are transparent are areas where we do not want metal wires. As with chemical vapor deposition, which we use to lay down polysilicon, when we use PVD, it's going to lay down a film over the entire wafer, and we cannot selectively choose where we want to lay down the metal. So we have to cover the entire wafer in metal first and then start etching the pattern on it. Now we will apply photoresist on top of the metal. We will expose the photoresist and we will develop it. This will allow areas that are transparent to be stripped away, and under the areas that are stripped away, we have metal exposed to the outside world. We can then use etching to eat away at the metal layers. If we are using aluminum as the metal of choice, then we can use dry etching to eat away the areas that were exposed. Dry etching is actually very good because it is directional, it does not eat laterally, but there's a problem with it in that it builds up a lot of static charge, which could lead to something called the antenna effect. In any case, what we have done here is that we have created a metal wire profiles. Here the metal wires are contacting the N plus area of the well. They're also contacting this this source or drain of the PMOS transistor. We're connecting two terminals of the NMOS and PMOS together using a metal wire. We have transferred the pattern on the mask down to the metal layer. And if we take a cross section and look at it, this is the cross section that we have managed to create. Now, when we think about routing is the process of connecting modules on the chip together. And when we go to the design flow, we will find that one of the most challenging steps in the design flow is placement and routing of modules. This means where do we place the specific modules and how do we route them together. Now, if you look at this situation, this very simplified situation where we want to route module 1 to module 2 and module 3 to module 4, we can do this using the method shown if we can create this crossover here. Crossover means that the two metal wires that we use for routing are not going to make a contact. Instead, they are going to cross over each other. If we look at the cross section, if the metal wires are all in the same layer, then whenever we cause them to meet, they will intersect. There cannot be a crossover, which is why all CMOS processes use multiple layers of metal. So we have metal 1, metal 2, and maybe metal 3 up to metal 8. We can have as many metal layers as the process allows. The multiple metal layers allow us to perform crossovers. In a more general way of viewing it, multiple metal layers allow us to route with more ease. They give us more degrees of freedom to route between the modules, which is why metals are never used in a single layer. There are multiple layers of metals. Each layer of metals is going to have its own mask, which is why the mask we used here was called the metal 1 mask. So this was the metal 1 mask. Now we're going to move to the metal 2 mask. Before we go to the metal 2 mask, just as we did with the metal 1 mask, we will use a contact mask first. So the contact mask that created contacts between N plus and P plus and metal 1 was called the contact mask. In this case, we use a mask to create contacts between metal 1 and metal 2. This is called a via 1 mask. Vias are contacts between metal layers. Some processes allow you to only create contacts between successive metal layers. So via 1 can connect metal 1 and metal 2. Via 2 will connect metal 2 and metal 3, and so on. If you need to make a contact between metal 1 and metal 3, they have to go through metal 2 first. So you have to use two vias. In any case, via K is going to create a contact between metal K and metal K plus 1. In this case, we are using the via 1 mask to create a contact between metal 1 and metal 2. We do it the same way we did with the contact mask. We grow a layer of silicon dioxide using CVD. We cover it in photoresist. We expose and develop. We use wet etching to open up the via. We have the same challenges. We have to etch long enough so that the via completely opens, and at the same time, we don't want too much lateral etching, otherwise we can create unwanted shorts. Then we move on quickly to the metallization stage, where we use PVD to deposit a thick layer of the metal. In this case, it's the same material we used to create metal 1. We just use a different color for it to distinguish the two layers from each other. And then we apply the metal 2 mask. We deposit photoresist, we expose and develop, and then we use dry etching to etch away all the unwanted areas of metal 2, and we create the pattern that we want. In practical CMOS processes, you can have many more metal layers. This is the final shape or cross-section of the wafer that we created. When the wafer is done, when the chip is done, we also deposit a very thick layer of silicon dioxide on the top, which is called the overglass layer. And this layer just has a protective function. It protects the components of the chip from abrasion or contact with the outside world.